Morning, everyone. I just asked, and we have the realization that this was drawn to be a likeness of me. I would like to say, though, that I typically wear shoes when I work. So, yeah. That was one time I had my shoes off, and that's because I got by the rain, okay? Trust me, I would much rather have had my shoes on than off, okay? Okay. Anyway, we are going to move on to unit, we're at 2.12, properties of logarithms. It says logarithmic function manipulation, but in all reality, the only reason why we can manipulate these functions is because of the properties of the logarithms that we're going to talk about. These are not all of the properties of logarithms. This is not a comprehensive list. There are others, but these are the three major properties of a logarithm. I don't need you to know their names. I'm never going to test you on their names, and neither is AP. And also, I feel like it's redundant to have written it twice, once for logs base b and once for natural logs, because natural logs are logarithms. They follow the exact same rules. They are log base e. So there is no reason why we couldn't have just had these three. So because of that, I'm not even going to mention those three. I'm just going to expect you to know that they are exactly the same thing. All logarithms behave by the same set of rules, and you should already know these rules from Algebra 2. Here's what this one says. If you have a multiplication in your argument of a logarithm, then you could say that that is the addition of two logarithms. Let me explain to you why. Remember that exponentials and logarithms are closely related. The logarithm is a way of solving for the unknown exponent, correct? But if you multiply two exponentials with the same base, you add the powers, right? If you multiply with the same base, you add the powers. This is the exact same rule. It's just in logarithmic form. So remember when we were writing things, oh, that's in exponential form, write it in log form, or that's in log form, write it in exponential form. This is the exact same setup. It's just using your exponentials laws in logarithmic form. So if addition in the argument leads to the, I said that backwards, I'm so sorry. If multiplication in the argument leads to the addition of logarithms, then it should make perfect sense why division in the argument leads to subtraction of logarithms. And just like when you divide two numbers of the same base, you subtract the exponents and it's always top minus bottom. For the logarithms, it will be log of top minus log of bottom. Okay? And lastly on this short list is, you know when you have a power to a power, you can actually multiply those exponents? Here your argument has a power. And it can be moved to the front to multiply the two things. And again, the reason why this works is because log of something is essentially the value of an exponent. So here's you multiplying two powers. Okay? Now, when I teach this material to Algebra 2, I often show them a couple things that look like they should have rules, but they don't. So I'm going to go ahead and show that to you as well, because I figure if it's good for them, it's good for you as well. Here's something that we have absolutely no way to clean up. Base B, whatever. I don't feel like writing the B. There is nothing we can do for that. Absolutely nothing. By the same token, if I'd put a minus sign in between those two, there's nothing you can do. Okay? Addition and subtraction in the argument cannot be manipulated in any way, shape, or form. It's a transformation of the graph, but it cannot be manipulated into separate logarithms. And another one that students will often try to do. Students will often try to set this up. But no, that's not true. Because we just saw what happens when there's division in the argument. So this is also not something that you are allowed to do. You will see this again. but it does not come from having multiple things in the argument. It comes from something else. Okay? Just wanted to put that out there. These rules are true backwards and forwards. So if you go from a single logarithm to multiple logarithms, this is called expanding. If you go from multiple logarithms down to a single logarithm, that's called condensing. And you might look at these next two boxes. This is expanding, this is condensing. So we'll be doing both things. And again, this is pure Algebra 2 review. It says expand using the properties of logarithms. What do I see? I see three objects held together with multiplication dots inside that argument. And every time there's a multiplication inside the argument, that can be split into the addition of two logarithms. But since there's three objects there, that's actually going to be three logarithms. And they will all have the same base. They're all going to be the common log base 10. So that gives me log of 8 plus, I'm making those red multiplication dots into red plus signs, log of x plus log of y to the fourth. No, that is not it. And the reason why? That log at the end has an exponent on the argument. Yep, we can take that exponent out of the exponent position of the logarithm and stick it on the front as a multiplication. So we can do the same thing here, take this 4 and put it right there. And this thing will finish out as log of 8 plus log of x plus 4 logi log of y. That is fully expanded. I am going to add a secret example C to this box. And I'm going to do it here, and we'll write it down here. So when we go to do this one, just don't write far down, because I'm going to add a third example in here that I want you to see. I'm just going to be picky here, and I'm going to put some parentheses on my argument. What do I see? I see a division in the argument. Division in the argument can be split into the subtraction of two logarithms. It's always top minus bottom. So we have the natural log of the square root of x squared plus 5, making that red division symbol into this red subtraction symbol, the natural log of x. And that is not all we can do. Who sees it? Who sees what else could be done? Alex? What exponent? The square root bar is an exponent. What exponent is the square root bar? 1/2. So this, good job, Alex, this very phallic looking thing I circled is an exponent that can be brought to the front. That is the 1/2 power. So what I'll be looking for now, which actually won't come across on the video very well, is I'm looking for a thumbs up, thumbs down. And my question for you is, and don't do it yet, my question for you will be thumbs up if you think we're finished, thumbs down. Actually, just put a thumbs up if you think we're finished. On the count of 3. 1, 2, 3. Thumbs up if you think we're finished. One person. Chris put a thumbs up. That was brave of him. You know what was funny was he looked around to see if anybody else was going to join him, and then he reluctantly put his thumb up and was reluctantly the only one correct. This is finished.
Why though?
But Mr. M, I see an exponent in that argument. I'm aware, but you might notice I said the entire argument has an exponent. That's when this rule can be used. This entire argument had an exponent. This entire argument had an exponent. This argument has an addition in it, and there is nothing we can do with that. Nothing. Okay? You know what? I told you I was going to add secret example C. I'm actually going to add 2 secret examples, C and D. Here is secret example C. I'm just going to use the common log because life is easy with the common log. I might have written that a little too large. I probably should have squished it so I had enough space to write 2 lines. Whatever, we'll make it work. We'll make it work. What you should be noticing is there's overall a fraction in the argument. So I could split that into the subtraction of 2 logarithms comfortably. That gets me log of A minus log of B times C. Now this is not finished. Reason why is because there's a multiplication in this argument. So then, who's brave enough to volunteer to tell me, other than Chris, Kaylin, I don't know if she's ever actually spoken to me in class before. Kaylin, okay, hello, nice to meet you. I'm Mr. McCutcheon. Hi. And you're not afraid of being wrong, right? Awesome, I love that. Okay, if you would please, tell me what you think this fully expands to. And I'm going to write down what you say. And I'm writing in pen, so please do me a favor, don't screw this up for us. No pressure or anything. Log A, okay. Minus log B plus log C. Is she right? So, unfortunately, she's not right. She says, bro, why are you writing it down then? But let me, now Kaylin, you tell me what went wrong. I'm going to have to scribble it out. I know you know, but I'm asking Kaylin. Would you like a shout out? Okay. Chris, you need parentheses around these 2 things because they were both in the bottom. And if there's parentheses around them and a minus sign in front of them, they both get that minus sign. Kaylin, thank you so much. That's why I said you're not afraid of being wrong, correct? There's a reason why I added this to the lesson. It's because it's a very commonly missed thing. And I was actually hoping she'd be wrong. That way we got to have the opportunity to talk about the parentheses. And then I get to tell you this. Anything that comes out of the bottom of the fraction in the argument gets the negative sign in front of it. But why? Remember, negative exponents go to the bottom, right? That's why this is a subtraction. It's as if both of these objects, if we could have moved them all to the top, and it could have said A times B to the negative 1 times C to the negative 1. And we would have had log of A plus log B to the negative 1 plus log C to the negative 1, and those negative 1 powers would have scooted to the front. Or we could do it like this. It doesn't matter. They're all going to land us here. So once again, watch out for these multiplications in the denominator. If it comes out of the bottom, it needs to be negative when you expand. Thanks, Kaylin. I appreciate you. And Alex, the reason why is because I was going to write the parentheses and then show you it doing that. That's why I said maybe I wrote this a little bit large. I had plans. Now I need to try to squeeze secret example D on here. And now that I've said that, I don't remember what secret example D was going to be. I don't know. I'm struggling. Oh, I remember now. I got it. Secret example D, which is actually a little bit easier than secret example C. I'll use natural log because why not? Natural log of square root of AB. Okay, we've already seen what happens with that square root bar. We know that that square root bar is an exponent, right? Okay. You have two options. Option 1, move that power to the front of the logarithm. But when you expand it, you must remember that both parts of that argument have that exponent, which means you would once again have to use parentheses if you did that and then distribute it. Option 2 is give the exponent to both the a and the b, then expand, then move the 1/2 to the front. Either way, both of these objects have this power. That means in the full expansion, both logarithms will have that power in front of them. I'm out of space, so I'm just going to go directly to the full expansion. There. I just needed you to see multiple objects in a denominator, multiple objects underneath the same exponent. I just wanted to make sure that you saw that happen. Yes, it could just be written 1/2 and then parentheses, but I would typically say you're not finished until you distribute. There's not a that's the correct way, but on my test it would look like that. And I would assume that AP would be looking for that as well. And the reason why is because we're gearing up for being able to solve logarithmic equations by factoring out GCFs and things like that. By contrast, I do think actually that condensing is easier because it's less likely that you're going to get caught with a oops, missed a negative sign, or oops, missed a distribution. Condensing is just expanding in reverse. When I was expanding these things, when it happened, what was always the last thing that occurred? When I was expanding, when it happened, what was always the last thing that occurred? What's the last thing that occurred here? What's the last thing that occurred here? Technically, what's the last thing? The exponent was the last thing that was occurring. When you condense your logarithms, you cannot have numbers in front of them. I'm only going to say it now because I don't remember if I said it earlier when I was looking at the actual examples. I mean, the formulas at the top of the page. You can only expand and you can only condense if the logarithms have the same base. I noticed everything here was log base b, log base b, log base b, ln. You can only condense if they have the same base because when you expand, they all have the same base. Just wanted to make sure I said that. We can do one more thing. The subtraction of two logarithms that have the same base, these are both log base e, is that what his name is? Closure property? Yeah, okay, closure property, yeah. The subtraction between two logarithms is one logarithm with division in its argument. So the ln of x to the 5th over, and you could say x squared y squared, or you could just say quantity xy squared. That one really doesn't matter. Except you could actually apply some properties of exponents here. This will simplify a little bit. Because here, when you divide two numbers of the same base, you subtract their exponents. So it's going to be most condensed and simplified if you say the ln of x cubed over y squared. There we go. Okay. That kind of thing is going to happen on the next one as well. It won't be a division though. Like we said before, you cannot condense logarithms if there's a number sitting in front of them. So you have to take this 3 and you have to move it to the power of the argument. I think that's easiest to understand if we put parentheses around our arguments. That way we don't think it's just being on the y, that it's actually on the x cubed y. And we'll do the same thing with this 2. It's going to go here. What I would do at this point is I would apply the exponent to the argument. And you can do that because that's multiplications in the arguments. When you raise a power to power, what do you do with the exponents? Oh, why did only one person answer me? This is an AP pre-calc class. When you have a power to a power, what do you do with the exponents? Multiply. Like the whole class said add. It's multiply. Oh gosh. Okay. There. Okay, now, because there's addition between these two logarithms, you get to multiply those arguments. Single logarithm. You know what? I didn't need the bracket. I'm just going to write it like this. Now, when you multiply two numbers with the same base, this is where you add, AP students. You add these exponents. I said I didn't need to use brackets. I thought I was going to do brackets and parentheses, and then after I drew the bracket, I realized I could just use the dot. So brackets and parentheses do the same thing in mathematics. It doesn't matter. X to the 9th, y to the 5th, z to the 4th. Boom. Yay, he says. Okay. Can I flip? Okay, that's why I ask. Flip it over. We're just going to do the back of this page today, and we will hold off on the second part until Monday. I would argue that this is one of the most important properties of logarithms. I say it's the most important part of logarithms, and like half the class didn't even look up, didn't even bat an eye at the fact that I said this is mucho important, and it's going to be very, very necessary for future skills. She's still not listening. Yeah, you, Alex, what are we doing? Well, I'll say it again. Arguably the most important logarithmic property there is. We want to make sure we all understand how to use this. It's called the change of base formula. What change of base formula allows us to do is write a logarithm in any base we want to. This is where you see log over log. And it only works if the logarithm on the top and bottom have the same base. Allow me to show you that you can manipulate it and write it in any logarithm that you'd like to. If I said to you, what is the ln of 5? And I just said, I want you to write this in terms of the common log. Then what you would have to do is you would have to go, all right, well, the natural log is log base e. Can we agree to that? So if I wanted you to write this as the common log, then it would be common log of 5 divided by the common log of e. Can we agree to that? Yes? Okay. E is a number. Why did I write it like this? Because what I wanted you to see was, and I know I'm kind of letting the cat out of the bag a little bit here, is what if it didn't say the ln of 5? What if it said the ln of x? Let's pretend it said the ln of x. And I asked you to describe to me what transformation occurs to the parent logarithm graph to turn it into the natural log graph? The answer would be 1 over log of e, which I have no clue what that is, so we're going to grab a calculator. It's second ln. This is roughly 2.303. So if you would like to turn this graph, log of x, into ln of x, all you need to do is perform a vertical dilation of factor roughly 2.303. And that would turn log of x into the ln of x. So the change of base formula is not only useful for evaluating logarithms, it's also useful for describing transformations. It's a big deal. It allows us to rewrite a logarithm into any base we want. Why would you want to rewrite this? I don't know. Maybe you do. But the point is, you could write it as the log of 5 over the log of 2. You could write it as the ln of 5 over the ln of 2. Heck, you could write it as log base 5 of 5 over log base 5 of 2. But what's log base 5 of 5? Well, that's crazy. Oh, I'm sorry. Crap, I wrote, man. Here I thought I'd written something profound, and I wrote the darn thing wrong. Look at that. Isn't that crazy? Well, that's wild, isn't it? Okay, I'll rewrite it. So yes, this calculator does have a log base function. If you scroll all the way down in the math command, it's there, right? And I go, let me see what log base 2 of 5 is. It's that. How about 1 over math log base 5 of 2. Dang. See? Isn't that cool? So change of base is a very powerful tool that allows us to write logarithms in any base that we would like to. And again, the reason why it's such a powerful tool is because of transformations and because it allows us to solve logarithmic equations by hand and get perfect answers. Yeah, they might have log in them somewhere, but the point is they're perfect. Okay? And eventually, we'll do that, I hope. And if I don't see anything difficult enough, well, I might just make up some of my own for funsies. So it says, evaluate these logarithms by changing the base. Obviously, we're going to use a calculator, but we're going to pretend that we didn't know how to find the log base function on our calculator. All you have to do is either use the common log or the natural log. It doesn't matter which one you choose. You'll get the same result. Just to prove a point, I'll use the natural log this time. Alpha y equals stack fraction, natural log of 13 over the natural log of 3. And then I'll do it again, but this time I'll use the common log. So you see they're the same answer. And that's not to say that the ln of 13 is equal to the log of 13, because they're not. But the ratio of their values is equal. Okay? A About 2 point, oh, we have to 3 sig figs, right? 2.33. No, that's IB. 3 decimals. 2.335. Man, that's confusing to me sometimes. 2.335. You can choose whatever log base you want. It doesn't matter. Yes, sir. For this one? Yeah, log base 10 of 6, which is just log of 6. So you could do 1 over the log of 6. You could do log base 2 of 10 over log base 2 of 6. You could do ln of 10 over ln 6. You could do log 10 over log 6. For funsies, I'll do log 10 over log 6. Oh, what is log 10 again? 1. So it's 1 over the log of 6. Either way. Because log of 10 is 1. There you go. 3 decimals, 1.285. You guys realize you don't need a calculator to do this next one, right? That the answer is -1. Do you see that? Because this is 2 to the -1. Okay, we already know the answer is -1. But just to prove a point, I'll use ln this time. Turdur. Isn't this easy? Isn't this fun? I love logarithms. I freaking love these things. They're some of my absolute favorite mathematics. They really are. I love logs. I love trig. And I love calculus. Okay, vertical translations using the product property. When graphing logarithmic functions in this format, where k is a constant, we can use that product property to say, hey, look, there was a multiplication in this argument. And since there's a multiplication in this argument, I can write it as the addition of 2 logarithms. But if k is a number, then log base b of k is a number that we're adding to log base b of x. That means that, and that's what you're seeing here, that means that a horizontal dilation of a logarithm is a vertical shift of a logarithm. Sound familiar? Yeah, kind of sounds like horizontal shift of the exponential could be represented as a vertical dilation of the exponential. Notice how it's the same rule, just said backwards. How about that? It's because they're inverses of one another. So stinking cool. Here, use the product property to show that it is a vertical translation of the parent log base 2 of x. Fine, easy peasy. The way we pull that off is, I'm going to find a color I haven't written a lot of yet. You know, I haven't started a question in green. Let's do this one in green. They're talking. I'm just going to keep writing. They're all talking about the Lorax. I don't freaking know. We put a purple dot. We put a purple dot right there. Write that as a purple plus sign right there. Oh, and by the way, what is log base 2 of 4? What does that equal? 2. It's 2. Because it says what power of 2 gives me 4? The answer is 2. So what I actually have here is 2 plus log base 2 of x. So it's clearly f of x plus 2. Multiplying by 4 on the inside, so a horizontal dilation of factor what? Horizontal dilation of factor 1/4. Remember, horizontal inside opposite. So this is a horizontal dilation. Factor 1/4 is the exact same thing as shifting up 2 units. They have the exact same results. It says graph both of them on the grid to the right. All right. I'll do f of x in, how about we do, oh, blue? Okay, I was going to do black, but he said blue. I was going to do black, but it's all right. Nick wants blue, so we're going to do blue. Log base 2 of x. We know that it is asymptotic to the y-axis. And we know log base 2 of 1 is 0. So f of x is going to have a x-intercept there. Log base 2 of 2 is 1, so it's at 2, 1. Log base 2 of 4 is 2, so I'm at 4, 2. Log base 2 of 8 is 3, so I'm at 8, 3. So there's f of x. Oh, crap. I always miss those dots. Logarithms are hard to draw. And we'll do g of x in green. Shift everything up to. Here, here. Uh-oh. I counted wrong. I said I counted wrong. Would you give me a move for 80 second? There. There. There's g of x. It says describe the change in the output values over equal length input values right at the end. Okay, you had a question for me, yeah? You wrote that 3 on the 9, wouldn't it be on the 8? 3 on the 9, wouldn't it be on the 8? Oh, these two dots you mean? Oh. You mean I just plotted wrong? Yes. It happens to the best of us. Sorry about that. Yeah, there's no dot here. Or here. Might be. Hate when that happens. Oops. What? I shifted the blue one up too. That was the whole point of part A, this guy. That's how. I just took all my dots and I shifted them up too. But his graph is bad. Man, I'm so bad at this job. Okay. Describe the change in output values over equal length input values. You know what the change in output values is? They're 2 more than the original. Add 2 to output values. That's not AP. Hey, let's write a rule just for funsies. You know what? I don't care what you write. I'm writing the rule. Well, I mean, you know what's interesting is for logarithms, 1/4 x, comma y is the same as x, comma y plus 2. So 2 different rules giving us the exact same graph. So neat. Okay, well, that's where we're going to call it today because I don't know if I can handle anymore.